In the 1970s, astronomers made an unsettling discovery. Our Milky Way galaxy is moving through space, pulled by invisible forces towards something we couldn't see. Our destination was hidden behind what astronomers call the Zone of Avoidance, a region of sky obscured by our own galaxy's gas and dust. Imagine drifting on a raft in a vast ocean on a moonless night, caught in a current heading toward an unknown destination. That's us, and we're not alone. All our neighboring galaxies are caught in the same cosmic flow. The first clues. Two teams of astronomers independently found the first hints of this great cosmic current. Brent Tully and Richard Fisher were using radio telescopes in Australia to map distant galaxies when they noticed something extraordinary. The galaxies they surveyed all seemed to be moving in the same direction, as if pulled by invisible chains. Around the same time, other teams studying the cosmic microwave background, the afterglow of the Big Bang, discovered something equally strange. This ancient radiation showed a temperature bias across the sky. It was slightly hotter in one direction and cooler in the opposite direction. Even after accounting for the sun's motion around our galaxy's center, a residual movement remained. Something was pulling the Milky Way and thousands of neighboring galaxies through space at hundreds of kilometers per second. We couldn't see what was pulling us. We couldn't map it or understand it. So we did the only thing we could. We gave it a name, the Great Attractor. For decades, this remained one of astronomy's greatest mysteries, a gravitational sink pulling our entire corner of the universe toward a single point in space, yet completely hidden from view, the history of motion. To understand the Great Attractor, we first need to understand motion itself. The history of science is really the story of humanity's growing awareness that nothing in the universe stands still. For millennia, the brightest minds in Europe and the Middle East believed Earth was motionless at the center of the universe. Then in 1543, Nicholas Copernicus revolutionized our understanding by placing the sun at the center with Earth in motion around it. But this raised profound questions. If Earth is moving, why don't we feel it? Why isn't there a great rushing wind as we orbit the sun? It took centuries and Isaac Newton's theory of gravity to understand that we don't feel Earth's motion because we're moving along with it. Space is a vacuum. There's nothing to push against. Einstein's theory of relativity took this further, showing that all motion is relative. There's no fixed universal reference frame. You can claim you're standing still and the universe is moving around you, and in a sense, you'd be right. Finding our reference frame. But the expansion of the universe gives us something special, a preferred frame of reference. The universe itself is expanding, with galaxies generally moving apart from each other. We can measure motion relative to this expansion, what cosmologists call peculiar velocity. And the universe provides us with the perfect ruler, the cosmic microwave background. This radiation was created when the universe was just 380,000 years old and fills all of space almost perfectly uniformly. Any motion we have relative to this cosmic reference frame distorts our view of it. When we measure the CMB, we find it's slightly hotter toward the constellation Leo and slightly cooler toward Aquarius. This temperature difference reveals our motion through space at about 600 kilometers per second. After accounting for the Sun's orbit around our galactic center and our collision course with Andromeda, there's still a residual velocity of about 300 kilometers per second, pointed straight toward the Great Attractor, your cosmic journey. Without taking a single step, you're moving through space at incredible speeds. Earth rotates at up to 1,600 kilometers per hour. We orbit the sun at 30 kilometers per second. That's 108,000 kilometers per hour. The sun orbits our galaxy's center at 230 kilometers per second. And on top of all that, our entire galaxy is being pulled toward the Great Attractor. For an average human lifetime of 80 years, you'll travel over 80 billion kilometers just from Earth's orbit around the sun. but the sun's journey through the galaxy adds vastly more to your cosmic odometer. Interestingly, the sun's orbital speed provides profound evidence for dark matter. When we add up all the visible mass in our galaxy, there isn't nearly enough to keep the sun in orbit at its current speed. Without an additional invisible source of mass, dark matter, the sun should have been ejected from the Milky Way billions of years ago. Yet here we are, held in place by the gravitational embrace of this mysterious substance.
The Andromeda Encounter. Our motion through the universe isn't random. We're on very specific trajectories, and one of the most dramatic is our collision course with the Andromeda Galaxy. Right now, Andromeda takes up about as much sky as your fist held at arm's length, but in 2.5 billion years, it will dominate our night sky, distorted by tremendous gravitational forces as it begins to merge with the Milky Way. It wasn't until 1957 that Dutch astronomer Hendrik van de Hulst measured Andromeda's velocity by observing radio emissions from neutral hydrogen. He found that Andromeda is moving toward us at about 300 kilometers per second. But this didn't necessarily mean collision. Astronomers can typically only measure motion toward or away from us, not side-to-side motion. It took until 2012 when astronomers used the Hubble Space Telescope to track thousands of individual stars within Andromeda to confirm we're truly on a collision course. The merger. The collision will begin in about 2 billion years. As our galaxies draw closer, tidal forces, the same physics that creates ocean tides on Earth, will stretch and distort both galaxies. Spiral arms may detach, creating vast stellar streamers called tidal tails. Bridges of gas and stars will form between the galaxies as if they're reaching for each other. When the merger finally happens in roughly 5 billion years, it won't be like a car crash. Most of each galaxy is empty space. The gas will tangle and form shockwaves, but the stars will mostly pass by each other like two swarms of bees interpenetrating. However, stars will come dangerously close to each other, disrupting their orbits. The orderly, flat disks of both galaxies will transform into a chaotic tangle of overlapping orbits. Some stars will receive gravitational boosts and be flung away from the merged galaxy forever. The collision will trigger intense star formation as gas compresses and fragments. At its peak, the star formation rate could reach 1,000 times what we see today. For a brief moment, it will be spectacular. Millions of newborn stars blazing bright white and blue across the merged galaxy. But then comes the tragic end. Galaxies have limited gas reserves for making new stars. Left alone, the Milky Way could steadily form stars for over 100 billion years. But the merger will burn through this gas far too quickly. Once those bright young stars die, there will be little gas left to form new ones. The merged galaxy, some call it Milkomeda, will become a giant red elliptical galaxy, slowly fading as its remaining stars age and die. Cosmic collisions everywhere. This isn't unique to us. Throughout the universe, galaxies are constantly interacting. The Mice galaxies, 290 million light-years away, have just begun their merger, their long tidal tails making them look like two mice nestled together. ARP 220, caught mid-merger 250 million light-years away, shines over 100 times brighter than the Milky Way from its intense burst of star formation. Galaxy mergers began billions of years ago and will continue far into the future. And our journey doesn't end with Andromeda. Our motion through the universe continues towards something much larger. Hierarchies of structure. The universe builds itself through hierarchy. Galaxies merge to form groups. Groups fall toward clusters, and clusters move toward even larger structures called superclusters. The nearest major cluster to us is the Virgo cluster, home to thousands of galaxies and drawing tens of thousands more toward it. In addition to our motion toward Andromeda, our entire local group is falling toward Virgo. This process began in the earliest moments of the Big Bang, but only accelerated a few billion years ago as Virgo grew massive enough to exert powerful gravitational influence. Laniakea, our cosmic home. For decades, astronomers thought we lived in the Virgo supercluster, a loose collection of about 100 galaxy groups spanning over 100 million light-years. But in 2014, Brent Tully and his collaborators revealed the truth using a revolutionary technique. They used mathematical equations originally developed for optimizing transportation of goods in revolutionary France, later applied to Soviet wartime logistics, and eventually adapted for cosmology. These equations allowed them to take current galaxy positions and velocities and reconstruct their motions through time, both backward into the past and forward into the future. What they discovered was stunning. The Virgo supercluster wasn't a supercluster at all. It was just one branch of a much larger structure. They named it Laniakea, a Hawaiian word meaning immense heaven. Laniakea contains 100,000 galaxies spanning over 500 million light-years, organized along 4 main branches. All of these galaxies are moving toward a common center, the beating heart of Laniakea, the final assembly point of a construction process that began billions of years ago. That center is the Great Attractor. The Norma cluster. The Great Attractor lies in the Zone of Avoidance, hidden behind the dust and gas of our galactic disk. But some wavelengths, radio, infrared, and X-rays, can penetrate that dust. Surveys in these wavelengths have given us glimpses of what lies beyond. At the heart of the Great Attractor sits the Norma cluster, several times larger than a typical galaxy cluster and about 220 million light-years away. Even at our speed of over 100 kilometers per second, the journey to Norma would take over 100 billion years. Beyond the Great Attractor. But the story doesn't end there. Recent observations suggest the Great Attractor isn't quite as great as we thought. Even accounting for dark matter, the Norma cluster's gravitational pull isn't quite strong enough to explain how fast we're moving toward it. There's something else pulling us, something even larger. The Shapley supercluster, over 650 million light-years away, is even more massive than Laniakea. Its immense gravitational influence affects every galaxy, group, and cluster around it for hundreds of millions of light-years. Some astronomers have even found hints of motion on even greater scales. In 2008, Alexander Keshlinsky discovered what he called dark flow, a large-scale movement of galaxy clusters at 600 to 1,000 kilometers per second toward a region between the constellations Centaurus and Vela. The puzzle is that there doesn't seem to be enough matter in any one place to explain such large-scale coherent motion. While debate continues about whether dark flow is real, it hints at structures and forces we don't yet fully understand. Echoes from the beginning. There are other forces at play. In 2023, Tully and his collaborators discovered that many nearby clusters and structures are arranged in a shell with a radius of over 400 million light-years. They believe this is a baryon acoustic oscillation, a fossil sound wave from when the universe was a hot, dense plasma just a few 100,000 years old. These sound waves were frozen in place when the universe cooled enough to become transparent, and they've been growing ever since. They named it Hole Lana, from a Hawaiian creation chant meaning murmurs of awakening from deep darkness. The dipole repeller. We're not just being pushed, we're also being pulled. On the opposite side of the sky from the Shapley supercluster lies a great void, one of many vast expanses of emptiness that dominate the volume of the universe. This dipole repeller doesn't just passively release matter, it actively pushes galaxies away from its edges, because despite its emptiness, it's filled with dark energy. And eventually, the repulsion of these voids will win. Einstein's blunder. In 1917, Albert Einstein made what he would later call his greatest blunder. He had just developed general relativity and decided to use it to describe the entire universe. But his equations naturally predicted a dynamic universe, one that was either expanding or contracting. This contradicted the conventional wisdom that the universe was static and eternal. So Einstein added a cosmological constant to his equations to stabilize the universe. A few years later, Edwin Hubble discovered the universe was indeed expanding. Einstein reportedly regretted his cosmological constant. But that constant never went away. In 1998, astronomers discovered that the universe's expansion is accelerating. The culprit appears to be vacuum energy, the energy of empty space itself. Einstein's blunder was actually one of his greatest insights. The rise of dark energy. 4 to 5 billion years ago, something fundamental changed in the universe. The expansion had diluted matter enough that a new force could emerge: dark energy. It had always been there, woven into the fabric of space-time itself, but it was weak compared to matter and radiation. Now, finally, it could take center stage. We don't definitively understand what dark energy is. We only know what it does. It causes the universe's expansion to accelerate, and its influence is growing. As the universe expands, matter spreads out and becomes less dense, but that same expansion creates more space and therefore more dark energy. Today, dark energy accounts for roughly 70% of all the contents of the universe. In the future, it will be 90%, then 99%, then more. The unraveling. Dark energy is already at work in the voids. These vast, empty regions are filled almost entirely with dark energy, driving them to expand and push galaxies at their edges away from each other faster than gravity can pull them together. The only objects that will survive are those already gravitationally bound, like our local group and clusters like Virgo. But the superclusters won't make it. Laniakea, Shapley, and all the others simply didn't have time to pull themselves together before dark energy began its work 5 billion years ago. The tragic end. We will never complete our journey. The Milky Way will merge with Andromeda, and the local group may reach Virgo, but will never make it to the Great Attractor, or whatever lies beyond. Billions of years from now, our motion toward the Great Attractor will slow, stop, and reverse. Over hundreds of billions of years, we'll watch distant clusters and galaxies dim and fade from view, slipping over our cosmological horizon as they're caught up in the accelerated expansion. Trillions of years from now, the mega-galaxy that was once our local group will be utterly isolated, adrift in a sea of darkness. Every other galaxy will have slipped away. But even then, motion won't cease. Random gravitational interactions will scatter stars away from the galaxy, one by one. Once they slip beyond its gravitational embrace, they too will be swept up in the expansion and flung away. Star by star, our galaxy will diminish. The same fate awaits every structure in the universe. Hundreds of trillions of years from now, every object will be completely isolated from everything else, separated by vast gulfs of faster-than-light expansion. The final rest. With nothing left in the wider universe, with no outside reference frames, with no stars to gauge motion against or cosmic flows to compare to, with no other sources of attraction or repulsion, the universe, what's left of it, will finally come to rest. We are creatures of motion, citizens of a restless cosmos caught up in flows and currents that began at the dawn of time. We're on a journey toward the Great Attractor that we'll never complete, pulled by forces we're only beginning to understand toward a destination we'll never reach. But for now, in this brief moment of cosmic history, we can look up at the night sky and know that we are moving, part of the grandest journey in existence, participants in the great cosmic dance that has been unfolding for billions of years and will continue for billions more.